Friends, today we are going to see some of the concepts related with bending of beam. Before going to start, we firstly see what we mean by a beam. A beam is a rod or a bar of uniform cross-sectional area. The area may be a rectangular or circular, and it is made up of homogeneous isotropic elastic material. So as shown in this figure, we take this AB as a beam. Usually in case of the beam, its length is much higher than its thickness. Now let us see what will happen if we apply the force or if we load this beam at two ends A and B by applying the external force. Here we see that when we apply or when we load this beam by applying external force, here we see that the filaments in layer AB will not change their length. So, their surface in which this filament AB is lying is called as the neutral surface. If we consider other filaments like A dash, B dash, which are above the neutral surface, then we see that there is elongation or increasing length of these filaments. Here we see that the arrows shown by blue are the direction of external force. So in upper portion we see that the force is acting in the outward direction, and due to the elasticity, the internal restoring force will be developed within the material in opposite direction of the external force. So in above the neutral surface, we see that the restoring forces are acting inwards. On the other hand, if we consider the filaments in lower portion of the neutral surface, we see that there is a contraction of the length, decrease in length of these filaments, and therefore the external forces are acting inside and the restoring forces are acting outside. So in above portion we see that the restoring forces are acting inwards, and in below the neutral surface the restoring forces are in the outward direction. So these two forces will form a couple. So we will see that in equilibrium the bending couple means the external force or the couple due to external forces is equally balanced by the restoring couple which is developed within the material. Let us consider one more definition, that is plane of bending. So here we have the neutral surface shown by a orange color. Now if we apply or if we load this beam at one end, suppose by applying the force in the downward direction, the bending of the beam will take place. So we are applying the external forces in the vertical direction, and therefore the bending of the beam will take place in vertical plane. So the plane which is shown in green color is nothing but the plane of bending, because the bending will take place in vertical direction. Now let us obtain an expression for bending moment of a beam. So consider a figure as shown here. Consider a small part AB of the neutral axis of the beam which is bent into a circular arc of radius r, making angle theta at the center of curvature as shown in figure. Let A dash B dash be another filament at a distance x from the neutral surface. Now find out the length of the neutral axis, that is equal to AB, which is nothing but r into theta. Now when we apply the external force on this beam, it gets bent, and we consider the filament at A dash, B dash. There is no change in length of the filament AB because it is lying in a neutral surface. But if you consider a filament A dash, B dash, which is at a distance x from this neutral surface, then there will be a elongation. If you consider any other filament which is lying just below the neutral surface, then there is a contraction of this length, that is decreasing the length of the filament will take place. Now let us find out what is the length of the filament at distance x from the neutral surface, that is the length of the filament A dash B dash, which is equal to r plus x into theta. Now we find what is the increasing length, that is equal to A dash B dash minus AB, that is equal to r plus x theta minus r into theta. Therefore, we will get the increasing length which is equal to x into theta. Now we define the longitudinal strain which is equal to change in length upon original length. Therefore, which is equal to x theta upon r theta, and which is nothing but x upon r. Now use the definition of Young's modulus. So Young's modulus y is equal to the longitudinal stress upon longitudinal strain. Therefore, we write down the longitudinal stress is equal to y into the longitudinal strain. Therefore, we get the stress is equal to y into x upon r. Now we try to find out the expression for stress. So consider a cross section EFGH of a beam as shown in this diagram. As we are considering a filament at a distance x of the bar, and this has the small area, suppose delta A. Therefore, the force which is acting on this area delta A, which is equal to stress into area of cross section. Therefore, this is equal to stress into area of cross section. But the stress is equal to y x upon r in equation 1 into dA. So this will represent the force acting on the area dA of the beam. And therefore, the moment of this force about the neutral axis can be determined very easily, and which is to be force into distance. So y upon r x into x delta A. Therefore, we get the moment of force about neutral axis, which is equal to y upon r x square into delta A. Now we will find what is the net moment of force acting on the layer A dash B dash, which is situated at the distance x. So that is nothing but y upon r summation x square dA. Now let us look towards the term x square dA. So this is similar with the moment of inertia of any body is equal to summation mi ri square. In moment of inertia relation, we have the mass into square of the distance. But here we find that this is the product of the area of cross section and the distance of the filament. So this also represents the moment of inertia. But here we are considering the cross-sectional area, and therefore the term summation x square dA is nothing but the moment of inertia Iz, and this is called as the geometrical moment of inertia of the beam. We use the word geometrical because here we are considering, instead of mass, we have the area of cross section, and this is also given by a k square. So k is nothing but the term like radius of gyration, which we have used in moment of inertia. Therefore, the bending moment of beam is equal to y ak square by r, that is equal to y iz by r, using equation 2. And this term yiz or ak square is called as the flexural rigidity of the material of the beam. Now let us consider two cases. The first case, if the area of cross section of the beam is rectangular, then we know that the moment of rectangular beam is given by mk square, which is equal to md square by 12. Here m is the mass of the bar and k is the radius of gyration, and d represents its width and breadth. So the moment of inertia of rectangular beam is always given by md square by 12. So from this relation we see that k square is equal to d square by 12. Therefore, the geometrical moment of inertia of the beam, which is given by ak square, and that is equal to, now area of cross section of the beam having breadth b and depth d is equal to d square by 12, which is equal to bd cube by 12, and therefore the bending moment of rectangular beam is nothing but y by r bd cube upon 12. So this is the bending moment in case of the beam having a rectangular shape. Now let us consider the second case. If the beam is circular cross-sectional area, or beam has a circular cross-sectional area, then in this case the area of cross-section is pi r square, where r is the radius of the circular beam and k square is given by r square by 4. Therefore, the geometrical moment of inertia Iz is nothing but ak square, which is equal to pi r square into r square by 4. Therefore, we get k square or ak square is equal to pi r raised to 4 upon 4. Now we substitute this value in this relation which we have obtained. Bending moment of a beam is always given by yiz by r, and therefore we get the bending moment of circular cross-sectional area beam, which is equal to yiz by r, which is nothing but y upon r into pi r raised to 4 upon 4. So in this way we can find what is the bending moment, or this is just like as a torque. So when we apply the external force, or when we load a beam at two ends, the moment of couple that will be created within the material of the beam is given by the above two formulas. So the bending moment depends upon the shape of the beam. So it is different in rectangular beam and it is different in circular cross-sectional beam. Thank you.